Oh,
It's me.
Okay.
Yeah.
Plug in.
Found the announcement, so I think. Yeah, that's the same one I used. Yeah, okay. Don't record yet.
Okay, we are recording. Good afternoon, everybody. I'm going to introduce Dr. Lisa Prato, and she graduated from the State University of New York at Stony Brook. And she had two postdoc positions at UCLA before moving to her current position at Lowell Observatory in 2004. Her research is primarily on young binary stars, from studies of their origins, evolution, and capacity for planet formation, to their exploitation as a means of measuring mass ratios and masses. Because most young stars are in gravitationally bound double systems, these are important research areas. And most of Dr. Prato's work exploits the power of high-resolution infrared spectroscopy, and she also uses photometry and interferometry and millimeter and visible light wavelengths. So please welcome Dr. Lisa Prato.
Thank you. How do I have a clicker?
Oh, no. You've got the,
Okay, arrows.
yes.
Thank you so much for the opportunity to talk with you and share some of my research. I find it really exciting. I hope you will. I wanted to I had this conversation earlier today with Ryan Mahoonan about all the detail, and I wanted to go into all the physics detail of everything I do, but then I wouldn't get the chance to talk to you about what my results are and what some of the the techniques I use, and so I didn't get as much of the physics as I wanted to. But rest assured, it is underneath everything that I do, and hopefully you will see that. I'll talk a little bit about it explicitly. I want to start by arrow. How come the arrow doesn't work? Oh, which arrow? No.
I'll try that one.
Nope.
There.
Okay.
I clicked on the mouse.
Okay. Really, I want to start by saying something about my team. I have all these great people who I work with now and who I have been working with for the last several years. This is just a few of the ones who most recently I've done research with. And some of you might recognize some of these characters because many of them were NAU students. And up at the top, do I have a mouse? I mean, a laser? No. Okay. Up at the top is Lauren Biddle. She did her PhD with me. She was an NAU grad student here. And Xiong Tang is over on the right there, underneath where it says talking. And Laura Flagg is up there at the top. She did her master's here with a Jenny Skolnick, but I've collaborated with her a bunch. Thank you so much. This is Noria Wright-Garba. She was a student with me a few years ago. After she graduated from NAU, she worked with me for a year and went on to a job at the National Solar Observatory. Ian Abeles did his bachelor's here. Tom Allen was my postdoc. Ryan Muzio was at RU here and is now in material science at NREL. So that's a good story. And then this is a recent photo from an observing run with my some of my current people who I work with, Taylor Kutra, who's my postdoc, Peter Knowlton, and Jacob Hyde. And Jacob did his bachelor's degree here too. So I'm very grateful to have all these smart, fun people to work with. And I really, some of the results were helped by work that they did that I'll be showing here. Okay, I always start with this slide because I always want people to define things, especially if it's not in my field. And I'm like, what? I don't necessarily know what that is. But this is Kepler's uphill battle because it underscores how when somebody's talking about, well, oh, well, there's orbits and they're elliptical and we can see planets. And so it's just a means of me saying, I'm going to define things. And if it seems like it's, you already know all this, but give me some slack in trying to make sure I bring everybody with me and sort of the details for the talk. So I'm going to start off with the driving questions, the big questions, and then talk about sort of the subset of big questions not capitalized that I'm going to focus on. Then I'll talk about the background, like the paradigm for star formation, binary star formation. And then most of what I'm going to talk about are fundamental stellar properties that we can get from binaries and why that's important and interesting. And then I'll say a little bit about binaries and planet formation. Okay. And I'll have a little summary. So context, the big driving questions. And every once in a while, when I was a grad student, and now I try to do this with people who I'm working with, you have to sort of step back and think about, well, why am I doing this? What are the big main things that are very interesting? Why are we doing physics? Why do we care about physics or astronomy or astrophysics? And so these are really tough problems. What is the nature of dark matter? What is the nature of dark energy? Right? I mean, this has to do with the sort of the fabric of our universe. Are the physical constants universal? Are they the same everywhere in our universe? Do they change? And people are doing observations to work on this problem. How did the first stars and galaxies form? This is tough because the first stars and galaxies, the first stars, all you had was primordial hydrogen, helium, and a little bit of lithium. So that's hard. It's hard for stars to form when you don't have some metals. And I'm hoping most of you who are physicists know that everything heavier than helium is a metal, right? Awesome. So when I say that to chemists, they freak out completely. And then how did the life-friendly Earth form? And is there life elsewhere in the universe? I mean, that's the one big one. A lot of people are looking for Earth-like planets because they're after that. But what I'm after is planet formation. And I get at that through sort of some different means, different approaches. And so really, it's how did I get here, right? So this is quoting from the Once in a Lifetime song from the Talking Heads. But that's, how did we get here? How did stars form? How did our sun form? How did our solar system form? How did our planet form? And so I back off from that a little bit and I look at how does our star form? How do single stars form? How do binary stars form? How many binary stars are there? How do planets form? What conditions produce terrestrial planets or any planets? How is water delivered to planets? Can planets form around binaries? And these are my motivating things that I'm going to touch on today. Single and binary stars, how do planets form? And can we get planets around binaries? And you might think, hey, we live here around the sun is a single star, no big deal, who cares about binaries? Actually, when I was an undergraduate, I thought they were like the most boring thing ever. Seriously, I was like, oh, a really stupid chapter of the book. But, now they're my bread and butter. Okay, so the young star binary paradigm. So this is the pillars of creation. This image just came out recently from the new JWST telescope. Pretty great. This is what I do. It's pretty fun. And what you're seeing here is stars, obviously, and you're seeing a lot of dust. Dust obscures things very, very well. And I'll prove that in just a second. But you're seeing these strange structures that are actually being blown apart. The less dense material is sort of blown away by photoevaporation from very hot, massive stars. And inside these sort of cold clumps, you have star formation. There's one sort of starting to peek out, that bright red blob. Where'd it go? See it on the screen. Up there, you can see something sort of embedded in there. So this is real, and this is real, and it's the same thing. So I tried to line them up, but one of them is, this one is the Hubble Space Telescope, optical light. This is the JWST telescope, infrared light. So what do you notice? It's where the stars go. Didn't kill them all off. this is a demonstration of how amazingly sensitive or how amazingly efficient dust is at obscuring stars. This is optical light. And in optical light, you cannot see through the dust. The infrared light, the longer wavelength infrared light, you're getting through the dust. So this actually, I love these pictures. So I'm like, okay, I'm gonna figure out a way to put these in. But I just wanted to show them to you because they're beautiful. These are star forming regions and they demonstrate something. But as I went through preparing the talk, I'm like, oh yeah, there it is again. The whole dust thing with optical and infrared. So that's part of why I work in the infrared. All right, here's Astronomy 100 in, let's do 45 seconds. So astronomers use the HR diagram. This is like basic. Many of you probably saw this in high school. But super basic astronomy, but it's incredibly powerful. We have this simple thing. We have this relationship between the temperature of a star and its luminosity. Like, yeah, big deal. But look, like all the stars, this main sequence thing, these are all the mature stars. These are all stars like the sun. They were born, they've grown up, they're mature, they're fairly calm, most of them. But they're all this thing called the main sequence. So there's this fun relationship between bright luminosity and cool temperature. Sorry, the temperature thing goes the wrong way, right? It goes from right to left. I don't know why, but that's how it is. So it's really nice. We have this beautiful relationship for stars. It's almost linear. It's a little bit of curve in it, but notice that the axis is not linear. But and then we have giant things that are very, very fluffy. That's a technical term, but they're very cool. And then we have white dwarfs, which are very, very hot, but they're very low luminosity, and they're actually very, very small. That's why. And these are end products of stellar evolution. Now we have another tool that we use a lot, which is the initial mass function. And this is a fascinating thing. No matter where you go in our galaxy, or how, as much as we can tell from other galaxies, if you count the number of stars, they all follow this power law function, the mass function. What I just put up here was Salpeter's first paper, 1955, with his exponent for the power law of minus 1.35, which is just this part over here. But it turns over, and you end up with this interesting region over here. We have substellar things and planets, and everybody's been fighting over that for many decades, but it's lots of exciting science in that. But this is this amazing thing that we can look at populations of stars everywhere, and they all have the same relationship. There's very few big ones, lots of low mass ones. I found online this fantastic mashup of the Hertzsprung-Russell diagram, mass function diagram, initial mass function. So this is brilliant because it's those two plots I showed in the last slide mashed up together. So here you see brightness or luminosity, and here you see temperature. But they put in another axis, which is stars per 10 to the 6 cubic parsecs. A parsec is about 3 times 10 to the 13 kilometers. So that gives you some sense of scale. And look, like just as you kind of saw from that plot of the initial mass function, but much more concretely, the massive hot stars, there's very few of them, and these red dwarfs and the K dwarfs, there's tons of them. And our sun is kind of average. But this is why I study low mass stars. There's lots and lots and lots of them. They're very influential. Yes.
Are you open to questions? I don't want to interrupt your.
Sure, go ahead.
Well, I just, the earlier Hertzsprung-Russell diagram was interesting, but one would think there'd be a third dimension on that. But and maybe it isn't important. You said mass is the most important thing. But isn't there a difference between metal core and metal rich stars? I mean, it seems like something should be going on with temperature and what is in the star besides just hydrogen?
Yeah, the stars, of course, have thermonuclear reactions inside of them, which are fusing the hydrogen and helium into heavier elements. And that's a whole other story, but I don't want to go into that too much today because I have a bunch of my research I want to talk about. But yeah, these very luminous hot stars are very massive, and these cool stars are very low mass. And so your mass determines exactly where you fall on this diagram. So high mass up here, low mass down here. And in the mashup that I just showed, because of the initial mass function, most of your stars are these very low mass red pool things. And yes, metallicity will make a difference, and it can shift things a little bit on that main sequence, but it's relatively small. And you make a great point, because the metallicity of something, how much, even in little teeny trace amounts, how much metals a star has, makes a difference in that star's life and evolution. But once that's set, mass determines everything else. Okay. Star formation. Okay, you just had the 45-second intro astronomy. Now you know intro astronomy. Now you're going to get star formation. And so this is a less dramatic picture, but since it's from a project I worked on, I wanted to show it. It's the circumstellar star forming region. And the dark stuff is, again, dust that's enshrouding these baby stars, these young stars that are forming in there. I'm looking at this region because we've been doing these, my colleague Travis Rector and I have been doing this very sensitive imaging to see evidence for jets and shocked gas in this region. And that's a tracer of star formation. But just a cartoon here to sort of walk you through what star formation is. So you have, in these very cold, dense areas of these clouds, you get gravitational collapse. It's very nice because you have these two things that are trading off against each other. You've got actually the motion of the gas, which is pretty cold, it's about 10 degrees Kelvin, and you've got the gravitational force that's pushing down on it. But the gas has some motion, and so you can actually think about it in terms of the sound crossing time. So you can think about how long does it take for information to cross the cloud. So if you have a little cloud core, and if you push on it a little gravitational perturbation, how long does that core take to stabilize against that perturbation? So that depends on the size of the core and the sound speed in that material. And so you can use that ratio to get the time of the sound crossing time. You can also think about the free fall time, gravitational free fall time, which is proportional to the gravitational 1 over the gravitational constant times the density of that material square root. And you put those two, you equate those two, and then you can solve for what how much mass and what size, given the density of the material, will actually cause the core to collapse. This is called the Jeans mass. But it's much more complicated than that, because inside the clouds, and there's all these other factors to take into account, but it tends to work out by all these complications sort of seem to cancel each other out. But once you reach that sort of critical collapse, once you have enough gas in a small enough space that you can collapse, you have this core forming, and then it gets hot. Initially it's 10 Kelvin, and then it gets hot enough to actually become a star, and turns on a deuterium burning. And so you create this energy source, and so you start to blow away this mantle around it. You start to rotate. At some point you have an angular momentum vector that comes into play. You have some kind of preferred rotational direction, and that holds that you end up having material falling down along that rotational axis to AU, which is the distance between the Earth and Sun. All right, the really, I said mostly H2 and dust. The component of the cloud is mostly molecular hydrogen and some dust. But I love this because in the years since Andrea Sola made that cartoon, we have observations that look exactly like his cartoon drawings. I mean, these are real. I mean, these are observations from various telescopes, Herschel, the VLT, and ALMA. So it works. Star and planet formation works. And so these are a whole bunch of images from the ALMA interferometer, the ALMA array, which part of it is shown here, all these little antennas. So it acts like one giant telescope, that you've cut pieces of it out, and you have to coordinate all that light and get it to use these beam combiners and delay lines, and you have to match up all the wavelengths. It's not that bad in the millimeter and submillimeter. It gets harder when you're working on optical wavelengths, and there are also optical interferometers. But it gives you the advantage of behaving like a giant telescope, and those array elements are mobile. You can move them around, and that has facilitated this amazing collection of images of disks around young stars at millimeter wavelengths. So these results from Sean Andrews' DKIS survey, which is phenomenal. I mean, there's gaps and there's holes and there's cavities and there's spiral structures and there's shock structures and there's inhomogeneities. And there's planets that are forming. Here you see a couple of ALMA images and an image of the infrared from the VLT telescope with a sphere instrument. And so you can see within the inner part of this disk, a couple of planets. This is PDS 70. You see PDS 70 PDS 70B and PDS 70C is over here. You see them all sending infrared, and they're actually accreting from the disk. These planets are growing from the disk material. So it's true, planets form in these disks around young stars. But binaries, right? So now what? Like, now what happens? Bad things happen. So people have imaged them with interferometers also. So you now see vastly more complex. It's not all beautiful like those nice disks I just showed. Here's more ALMA data from Rota et al. A couple of years ago with some binary systems. And you notice they're not, the disks aren't the same in some cases. Oh, and there's triples. Yeah, actually that's a quadruple because East is itself a binary. And so you saw this interesting things going on, right? U-iota rega, T-tau, those are both very complicated systems. Another triple here, HK tau. So I am going to try to get to those a little bit at the end of the talk. But I just want to say one last thing in this intro part, which is how do we know, maybe binaries are just a few here and there, we don't have to worry about it. No, there's a lot of them. And they tend to get more common as you go to, this is mass on the x-axis and multiplicity frequency on the y-axis. So there's more and more and more as you go to higher mass stars. But even in these low mass stars, there's a lot. And in the star forming regions, there seem to be even more, an overdensity. All right, fundamental stellar properties and binaries. So in my abstract, I said something about taking advantage of binaries to learn fundamental things. So I'm showing this slide again because, yeah, I want you all to know mass is the most fundamental thing. And as the question I had earlier was indicating, it does matter what your composition is. You set your composition, and then after that, your mass is everything. So your mass determines whether you die as a star, going off into white dwarf land and cooling off over the age of the universe, tens of billions of years, until you become a black dwarf and there's no energy left in you at all. That's very, very slow evolution. Or if you're on the more massive end here, bad things can happen in as little as 10 million years. You can become a supernova, and you can end up as a neutron star or a pulsar, which is a rotating neutron star with a jet that's beamed in our direction, so we actually see it, or a black hole, or nothing. So this is the Crab Nebula, famous supernova remnant, and tremendous structure and tremendous energy that was communicated, that was translated into that nebula at the time of the supernova. So yeah, mass matters, and how you die as a star. Mass matters and how you form planets. I just like this slide because it shows you this range of masses. So it's solar masses, this little symbol here. So 1, 2, 3 solar masses. And then the rows are different disk masses. So there's a correlation actually between stellar mass and disk mass. Disks tend to be more massive around more massive stars, but they might evolve more rapidly, right? the disks over here, this is time on the x-axis. And so the disks for these more massive stars evolve quite quickly. But these lines are just, the red line is mass accretion, how much mass is coming from that disk onto the star. And the violet and blue lines are mass loss through far ultraviolet and X-ray mass loss mechanisms. Okay, so stellar mass is important for how your disk evolves, and that's very important for how much time you have to form a planet. And then there's people who are trying to come up with calculations to show us how things evolve. Like all the rows on this table here will be a test afterwards. All these rows are different models from all these different groups, right? And so they have different mass ranges that they're looking at. Some of them are very low mass, like this first one, 0.001 to 0.075. Those are just brown dwarfs and planets. Some of them are much more massive. This one is 0.075 to 27. So there's all these nice models that people are working on to cover different mass ranges. People use different metallicities for the sun. So that's generally, the iron over the Fe over H, iron over hydrogen abundance. The Y is the helium by mass abundance for the sun. So look, everybody's using different initial conditions. They're covering different ranges in age. So there's all these models, there's all these conditions, but we don't really have many calibrations. You have to calibrate them. You have to have dynamically observed absolute masses to calibrate these. So this little, again, I show the HR diagram, this little blow up here on the right is the three different sets of tracks from Barath et al. 2015, from Fiden 2016, and then some updated tracks that Fiden has online. And they're all the same sort of low mass stars, half a solar mass. The vertical lines here are called mass tracks. It's how a star evolves in its mass as it ages. The top line here, the sort of diagonal, is 1 million years, 3 million years is the next one, and then 10 million years is the lower one. And so those are called isochrones. And so this shows you how a young star would evolve. But if you go out and you want to, like, you're dying to know what some stars' potential disk mass might be, because you want to know how likely it is that star will form planets. And so you go out and measure its luminosity, you measure its temperature, you stick it on here, you're like, oh, well, whose tracks do I use? So for anybody to develop realistic tracks, we must measure masses. These tracks depend on how they treat the opacity, right? The opacity is simply how easily or with how much difficulty the light gets out of the star because of whatever's in the atmosphere, what the temperature is, what kinds of molecules you have, what kinds of states that the atoms are in, what kind of transitions are possible. The equation of state for the stellar interior, everybody uses different equations of state, and treatments of magnetic field. So there's all these variables in these models. So absolute mass is really important, but mass ratio, if you want to understand populations of binaries, and I hope you believe me that there's lots and lots of binaries out there, and so we can't ignore them because everybody does because they're a pain, but you shouldn't because they're important, because they're a huge component of the stellar population of the universe. And so mass ratio distributions can help you to understand how binaries form. And we would like to know this because there's so many of them, and there's some problems with understanding that formation. So these are different, there's different metallicities here. The different colored histograms are the models for the different metallicities. Metallicity is just this Z in terms of solar metallicity along the top. And you see this black histogram, that's comparison to observations. And I don't remember what the pink ones were, but these are just the kinds of models you can simulate with different kinds of calculations in order to try to see what these mass ratio distributions are like. But what I want to do is actually measure what they're like, so we know what they're like. for these young stars. Okay, now if you want to go and measure mass, you have two choices with a young star. You're very lucky with a young star because then you can use that disk. You saw that there's the images I showed you from the D-Sharp survey with all of the beautiful disks and rings and everything. That was millimeter continuum. That was dust. There's also carbon monoxide, and there's other things too. There's all sorts of molecules in these disks, and you can use the Doppler shift of the molecules spectra at different radii through the disk in order to measure just the Keplerian rotation. So what do you get when you use Kepler's laws to something that's rotating around a central mass? You got the mass, right? It's very simple, nice physics. The other way you can get mass for young stars is spectroscopic binaries. This is supposed to be moving, it's not working, and I'm really bummed out because I kept sitting there running them online. But anyway, this is very basic. This is also the way we see reflex motion from exoplanets, but it's just the red star is more massive than the little yellow star. They're both orbiting their center of mass. And if you're taking a spectra, if your eye is down here at the lower left, and you're taking spectra at all the different locations as the two stars orbit the center of mass, right here where their position is now, they're perpendicular to your line of sight, so there's no radial velocity change. And so their lines are all on top of each other. But once the red star is on the left, the yellow is on the right, the lines split because one is blue shifted, one is red shifted, etc. And you see that 1889 observations of Theta Auriga. Thank God we don't have to use photographic plates anymore. But there it is. This is binary. There it is when the two components are perpendicular. Here, when the two components are one going towards you, one away. And Tony Amwari worked on this from 130 years ago. It's pretty cool. So here's a more modern observation from some work of Willie Torres, where even with not very good signal to noise, at this epoch, the two stars were perpendicular to the line of the sight, and here they're one's redshifted and one's blue shifted. And so, great, we can actually measure the velocities, and big deal. But when you do that over and over and over for the same star, you measure 5, 10, 20 radial velocities of the two components. You see the line split. You measure each one's velocity. Then all you do is apply these really simple equations for if you only see one star. So think about it. If the secondary star is very small and very low mass and very faint and very red, you're not going to see it because it's just, the spectrum is just swamped into the noise of the primary. But that's a single line system, and you can still get the mass function from that. And if you still can guess M1, numerically, you can solve this. So the P is the orbital period. If you keep looking at the same system over and over, you'll see it repeat for the same set of velocities, so you can get the period. The K is the semi-amplitude of how the velocities change. I'll show you that graphically in a sec. E is just the eccentricity of the orbit, which you can get from fitting the orbit. So you can get the mass function for a single line, and then you can play around mathematically and make some guesses at M1 or M2 and get some more information out. But what you really want is a double line binary where you can see the lines of both stars. And then you have not only the velocity semi-amplitude of the primary, you also have that of the secondary, and then you get the mass ratio. So I routinely measure the mass ratio of stars that are 400 light years away in the Taurus star forming region by using it. It's so cool. And I don't know, it's easy, but it's cool. So here's K1 and K2. So single lined and a double line. So you look at the peak to peak velocity. This is radial velocities on the y-axis, and phase is shown here on the x-axis, but it could be just time. Same concept. And you just take half of that peak to peak amplitude is your semi-amplitude. And then for your secondary, it's down here. Oh, shoot, sorry. I drew these wrong on this right-hand side. The secondary is the big one. The primary is the little one. My bad. Oh, and so each of these points, for example, on the left here, each point here is a spectrum. And so that's like 2 or 3 dozen spectra. That's a lot of telescope time, but it's worth it if you can measure mass ratios. But there's a problem if you have only optical spectroscopy. because just think about the way the Planck function works. And so here's two Planck functions for temperatures of 4,300 and 3,000 Kelvin. You have flux on the y-axis and wavelength. And the optical wavelength is in microns. So optical is over here on the left at 0.5. And the flux ratio, just given the behavior and the exponential part of the Planck function, the flux ratio is like 20 or something. I mean, it's huge. It's 24. But if you go into the infrared, then you've got this rate level. In the infrared, you're down on the Rayleigh-Jeans part of the Planck function. So now your flux ratio is only 3. So you can actually see the lines of the secondary. So the infrared is much better. If your two stars are not equal mass, the infrared is much better for actually measuring the lines, the spectral lines of the secondary as well as the primary star. Furthermore, remember that the Eagle Nebula Pillars of Creation slides that I showed? Think about the one that was taken in the infrared. All the dust that was obscuring in the optical, you saw right through it. So in these star forming regions, it's a lot easier to see through into the cloud if you're working in the infrared. The scene is superior on the Earth because in the Earth's atmosphere, you have these turbulent cells. That's what gives you, when you look at a star and it twinkles, it's the motion of those cells, those atmospheric cells that cause you to have seeing. When they're very turbulent, the seeing is terrible and the star is twinkling a ton. And on a very still night when the atmosphere is well behaved, the star is very sharp. So the seeing actually is proportional to how the size of the wavelength of light compares to the size of those cells. So the small cells interrupt or perturb the optical light much more extremely than the infrared longer wavelength light. Okay, so some of the places that I've gone to do this observing, a lot of it, well, this here is from the IRTF, the Infrared Telescope Facility. It's a 3-meter telescope on Mauna Kea, Hawaii. And that's Seashell, which was the first high-resolution infrared spectrograph that I used. They retired Seashell about 6 or 7 years ago. And I told them ages ago that, well, don't ever throw it away. So they sent me an email, they're like, you want it? I'm like, yeah. I'll come and get it. So I did. It's out at Anderson Mesa. And I'm still trying to figure out how to resuscitate it, or actually get somebody who knows what they're doing to resuscitate it and put it on a small telescope. But I own it now. So that's Seashell. I mentioned Igrins to some people earlier. This is the back end of the LDT telescope, Lowell's 4.3 meter, and that's Igrins, which came for 3 visits of 6 months back in 2016, 2017 through 2019. And that was pretty great. The instrument that I've used and I'll talk most about today is NearSpec. It was built by Ian McLean at UCLA about 20 years ago, and he put it on Keck. And that's the 2 twin-meter Keck telescopes. That's, which one is which? I think that's Keck 2 there. And this is like, I just like this slide a lot because it's an optical telescope. It has a high resolution shell spectrograph on it, and I've used it probably hundreds of times because it's great for doing long-term radial velocity surveys if you're looking for planets. And my team has been doing that for many years. And this is Peter and Jacob down here, and Taylor postdoc is taking the photo. And so I've used that for spectroscopic binaries as well. Sorry?
Is medium infrared or far infrared?
Oh, near infrared. 1 and 2 microns. Yeah. Oh, and here you are. So here at the bottom is the wavelengths. So these are the standard stars that I've been taking with NearSpec. I took with NearSpec and Keck quite a while ago, and just been using these as radial velocity standards and spectral standards for a long time. So how do we get radial velocities out of a spectrum? I mean, you just take a ruler and be like, well, it looks like it's on this. We have to go through a lot of stuff. We have to correct for the Earth's motion around the sun. You have to correct for the Earth's rotation. You have to get it right, those corrections. And then you have to somehow figure out a quantitative, precise way of getting the velocities. And so here's what I do. I take my standard stars and this is another talk, but there's also synthetic standards, which people create from models of stellar atmospheres, which are extremely useful because they're perfect signal to noise. But you take a couple of standards, you think, okay, well, my primary star, I think, for maybe from the optical spectrum is a K5. That's just a temperature. Astronomers use this crazy system of temperatures according to these spectral types, which is not exact. So trying to get away from that, but you can estimate the temperature of your primary star and what spectral type it is, and you take a guess at your secondary star. Then you take your primary star spectrum, your template, your secondary star spectrum template, you add them together at some velocity shift, and you get a model. So now you have your binary star model. Now you have at the bottom your observed young star spectrum, and you cross-correlate. And you step through all the different velocity combinations that you think are reasonable. And you do hold, V1 constant, change V2, et cetera. And you end up with this, effectively, this function of correlation coefficients for all the velocity steps that you've gone through. So just the primary and secondary velocities on the axes. And then you choose the maximum, and there's your velocity for both stars. Where the optimization of the correlation function. So then I can take things like simulations of mass ratio distributions, and I can show you a mass ratio distribution. This is very interesting because it illustrates how if you just look at the spectroscopic binaries from these close binaries that I'm measuring the velocities for, if you just look at them in optical light, you get this gray histogram. If you go to the infrared, you can get way down in the small mass ratios. So that's demonstrating the power. But then you can compare to people's simulations and calculations, and then you can help solve things. But mass, what we really want is mass. That's the gold standard. So how do you get mass, absolute mass of each component? Mass ratio is great, it can tell us a lot. How do we get the mass? There's a few different ways. See if the movie works. It's another movie. No. Oh, well, whatever. There's a few different ways. One is from looking at occultations, looking at eclipsing systems. So you have two stars, you've measured their spectra, but then you notice from the photometry, photometry is just flux. It's just how much flux you're getting from the system. You notice these little divots. When the smaller star goes in front of the big one, you have a big drop. And when the big star is in front of the small one, you have a small drop. So when they're orbiting right in your line of sight, they eclipse, they go behind each other. And so you see the light come and go. And that's great, because what you get is, for your equation here, the difficulty with this equation, you can get the period, you can get that velocity amplitude, you can get the eccentricity from the orbits. But how do you get the inclination? How do you get the inclination of that binary orbit? This is one way to do it, because you know the inclination is 90, because that's why the two stars are going in front of each other. You can get, I've mentioned this before, the Keplerian motion of the circumstellar disk, but you can have circumbinary disks. Lots of systems of close spectroscopic binaries actually have circumbinary material. So you can do this trick. You actually map out for all the different radii, you can map out the motion of, say, carbon monoxide in a disk. On the X and Y axis here, just arc seconds. So this is actually an image, and it shows the red shifted and the blue shifted carbon monoxide. And this is just the radial velocities I had for this particular star. This is UZ tau east. Conceptually, this is an artist's illustration, but conceptually it looks like this. You have the disk going around the two central stars. So you can solve then two equations, two unknowns. If you have some really great fancy stuff, an interferometer or adaptive optics imaging, you can actually image some binary systems. This is DI tau. My grad student Xion Tang published this paper last year. It was crazy because it had been found in 1990 from a lunar occultation where Wenping Chen, who actually was Xion's master's advisor, so it's kind of a nice symmetry to this. Wenping was using lunar occultations to look for multiplicity, and he saw it. And then Andrea Ghez looked at it with speckle interferometry, and she saw it. And then nobody saw it for years and years and years until she figured out from the radial velocities that there was some motion going on with the primary star. And so we went back and used adaptive optics, and we got a couple of observations and confirmed that it's a binary. But we actually have some degree imaging for the orbit, but it's all of these little gray lines are showing that there's scatter in the best fit orbit because we do not have enough coverage. But usually we can get systems where we do a lot of intensive observing, where we can map out the whole orbit. And the radial velocity curves here, again, it's bootstrapping to get the best method, the best result. Okay, so now I want to say something about planet formation. Good, I have a little bit of time. And this is, one thing I want to just point out, I meant to say this earlier. A lot of the time people were saying, oh, most of the systems, most stellar systems are binaries. That's not quite right. Most stars live in binary systems, but the distinction is if you count up the stars that are shown in this little cartoon on the right, the binaries have little ovals around them, and you can count the number of systems, and most of the systems are single. So 1, 2, 3, 4, 5, 6, 7, 8, versus 5 that are binary. But the stars are mostly in binary systems. So that's just a subtlety that I want to comment on. So if you say, oh, most stars are binaries, people go, no, that's not true. And they're correct. But it is true, I believe, that most stars live in multiple systems. And we get triples and quadruples. All right. So how are those separations distributed? Everything I've been talking about is spectroscopic binaries, things with really short periods of days or weeks or maybe a couple of years. But that's only this one section of this distribution plot. You only have, that's the spectroscopic close binaries are just this little tail end down here. But most of them are over here. These are a bunch of different binary separation distributions, depending on whether it's a star forming region, like Titari star forming region, with the young stars, the disks that I look at, or whether it's a young cluster where they've already evolved and they no longer have disks, or just the G dwarf population in our local local galaxy. So they're just different observed binary separation ratios, but nevertheless, there's a whole bunch of them in there, and they're 10 to 70 AU in the peak, which means sort of the scale of our solar system, right? Pluto is 40 AU away from the sun. So what happens with these binaries? There's a lot of work has been done on looking at unresolved binary systems to see, do they have disks? You know, what's going on? Do they have planets? Do they have disks? What's happening? And so Adam Kress and a couple of nice people have been doing this kind of work for decades, and Eric Jensen started this in the 1990s, but Adam Kress has this nice plot where he shows in terms of separation. So again, 1 AU is the Earth-Sun distance. So these really close binaries for disk frequency are much less than the wider ones. So that makes sense, right? The two disks maybe interact and rip each other off. But he also looked at binary systems with planets, and found that this red histogram is the distribution in the binary separation, again on the x-axis. It's the distribution of binary systems that have planets, and then this is the overall expected binary distribution just from the field. And so there's a deficit here. So clearly not as many planets form in binaries, and the disks in binaries seem to be less frequent for these very young binaries. And that makes sense. But the interesting thing is, why do we have any disks in binaries? Why aren't disks completely wiped out in binaries? Why do any of them survive? And so that's the question that we're working on. One of the questions that we're working on right now. And so this is, this just went into press a week or two ago, and it's sort of a combination of spectra that I've been collecting on, not spectroscopic binaries, because those are just too blended, that unless you have some super duper interferometer, it's very hard to like separate those and get an orbit like that one I showed at DR tau. But the ones that are a little bit wider, maybe 40 milliarc seconds, 80 milliarc seconds, you can use adaptive optics on Keck with the near spectrograph behind the adaptive optics system, and you can actually separate out the spectra of each star. And then the black lines superimposed on these are, you take some kind of synthetic model for stellar atmospheres, and you can actually model all of the properties of a star. You can model its temperature, you can get its magnetic field strength, which is crazy for these young stars, they're like 2,000 or 3,000 Gauss. You can get its rotation velocity, you can get its surface gravity, which is fluffy because they're young, they're still contracting. So you can get all this information from these infrared spectra. And for this case, we've mapped out part of its orbit. It's a pretty long period orbit. So you can see from 1990 to 2020, it's maybe a quarter or a third of the orbit, but still that gives you some constraints on the dynamics. You can also use the radial velocities of the two components combined with the orbital information you have. And here is, we also applied for ALMA time with looking at the millimeter emission for the two components, and you can see that they both have these cool dust disks in the millimeter. And it seems from the inclinations of the disks and the orbit, it seems that the disks and the orbit are all coplanar, everything's well behaved. And so we have two disks, and there could be planets forming. Now, DF tau, on the other hand, is a star that I looked at a few times. My former postdoc, Tom Allen, wrote this paper a few years ago, and he showed that if you look at just the photometry, just the brightness of the two stars in DF tau, it's really close. It's like 0.1 arcsecond. So you need you need Hubble Space Telescope, and you need adaptive optics to get this, just the fluxes of the two stars at different wavelengths. This is called the spectral energy distribution. You see in the ultraviolet, the secondary has no ultraviolet excess, and it doesn't seem to have an infrared excess. So we said very, very strongly in this paper, there's no disk around the secondary. And we've been following this orbit for a long time. Some other people were taking data on it in the 80s and 90s, and lately we've been taking data at Keck, so we have a very good orbital solution. And I got spectra, which we published initially in Tom Allen's paper, but now we're looking at again because we got ALMA data on this too, and it shows the disk around the secondary in the cool millimeter dust, which is pretty far out. I mean, there's clearly some kind of a central cavity, but there's this great question. These two stars have very, very similar temperatures. If you look at these line depths, they match up really well. So why is one of them have this cavity in the middle and seems to be, it has still dust around the outside, but it seems to be evolving faster. So that's the question. And Taylor Kutra is working on a publication of this beautiful ALMA data that she resolved a couple months ago. All right. And all these spectra are available in on our database, which is a work in progress. So if you go there, we're still filling this in. We're using the synthetic spectra to measure all the properties of these. But it's quite a long database. It has all of our, or not all, but it has a bunch of our Taurus targets in here now. You can click on the different links and look at the spectra. You can download the spectra and play with them yourselves. So that's work that Jacob Hayden has been leading. All right, so quick summary. Young binaries are common and they're complicated. They're also really, really useful. Spectroscopic binaries can give us these calibrations of these key models of stellar evolution. The mass ratio distributions can tell us something about how the binaries formed. And by the way, going back to those models of stellar evolution, once we've calibrated them, you can use them for single stars. They're not only for binaries. It's like orange juice. It's not just for breakfast anymore. They're the calibrations. They're not just for binaries. They're for any star, any young low mass star you can stick in there. And then close pairs inhibit circumstellar planet formation. But some planets still do form, and we're thinking that maybe is geometry, and, alineation, what's it called? Coplanarity that plays a role in the stability of this. All right, so I'll just leave those up and I'll take any questions you might have.
Good. Let's start with the students. Carlos.
All 3 weeks I worked on a paper published in the Statistical Journal, claiming the universe is about 2 times older than the weight of by standard model. That said, I would like to ask you, how would this new age affect the star formation timeline?
That's interesting. You know, it's funny, I just saw a paper recently that said we've gotten our young star ages all wrong too. It was also kind of a factor too. But it wasn't age of the universe. It was local to the young stars themselves. I don't think it would be a problem. I mean, I didn't get into this, but measurements of young star age are really hard. So you can calibrate those models in terms of mass dynamically very easily. Calculating them in terms of age it's going to be an exercise in relative age. So I think what we are most interested in is how much time does a star have disk material around it from which to form a planet? So that I think those relative age bins aren't going to change because of the age of the universe being much older. But that is really interesting.
Viserys.
Yeah, thank you for the good talk. What would you say after mass is the second most important stellar characteristic in terms of life and death?
Wow. I love that. I haven't thought of that. Let's see. I think that the rotation rate is a very interesting thing. So V sin I. So I think I used some jargon that I didn't define. So sorry about that. So V sin I is the stellar rotation modulo the sine of the inclination of the star, right? Because if it's full on, you can't see any rotation at all. But if a star is rotating rapidly, it tells you something about its formation. There's all these other things I didn't have time to get into, like the strong magnetic fields in these stars can lock into some ionized material in the disk, and you have what's called disk locking. And so the disk actually kind of grabs the star and slows it down so it doesn't rotate so fast. But so when you see a young star rotating really rapidly, you know something about the disk evolution, possibly, or the accretion time scale, because you throw a lot of mass on there and it will spin up for conservation of angular momentum. But I've never thought of it in terms of the full evolution. Maybe environment, which I didn't talk about at all.
Thank you.
I like that. I'll think about it some more.
Dylan.
Dylan?
Yeah.
So that was very, very interesting. As far as looking at the spectra, something turned out to be one of those triple or quadruple systems. I imagine that would be very chaotic spectra to try and compare a model with. Have you run into that?
Yeah. Yeah, Peter Knowlton was just showing, we're going through some of the spectra that he reduced from observations I got like a couple years ago. And he's like, okay, well, here it is with this great new model fit. And I'm like, oh God, there's something really wrong. I'm like, oh God, it's another spectroscopic binary. So there's all these beautiful binaries that I have in my sample. And then like nobody's ever resolved them before because nobody's taken the adaptive optics system and gotten the telescope time, observed them and deconvolved them. And like, I got the observations and she's done the data reduction. And yeah, I think a lot of them actually are spectroscopic binaries, which is a huge bummer because I wanted to use the simple binaries just to get some insight into how those properties are different in systems that have or don't have disks. And yeah, so it's challenging.
Dylan.
So my question is that you are stating well the evolution of transition stars, binary stars, the mass distribution, the results. I just want to know, I think it's nice that it feels like it's very complicated and just want to see so and find out everything is complicated. Is it that easy to get the result that you can?
Is it that complicated? You know, I don't think it's that bad. If I had my own telescope, it would be great, you know, if I had a dedicated telescope with, you know, poor old seashell who's languishing in a closet. I think a lot of what I described is time domain, which means observations that get taken of the same object over and over and over and over and over, which people are like, no, you know, we've had enough view with our telescope. So I think a lot of it is access to being able to take repeat observations and to really, you know, all of these things that I described can be sort of pipelines, can be made into something pretty smooth. And you know, people working with me are doing that with some of the stuff. And so it's not maybe as bad as it sounds.
Jorge.
Hi, regarding the frequency of single and binary systems, is it possible that a binary can merge into one system and survive?
Survive as a star, you mean?
Yeah.
I think those are, what, I think those are, I think that's bad. So that gamma reverse, is it gamma reverse? It's something like, I think it's the gamma ray bursts that are, stars that, well, and that happens, for sure it happens, because think about it, two stars, probably not these young ones, but maybe when they grow up, right? So think about two stars post-main sequence. So post-main sequence, what happens is you run out of all your hydrogen in your core, and you have to start using helium. But the changes that are that happen in the core of the star in response to the depletion of nuclear materials cause the outer layers of the star to puff up, and you got a red giant. Now imagine if you had one of the first spectroscopy binaries I worked on has a period of 2.4 days. So when that system grows up and it gets to be puffy, now you have the atmospheres of those stars. It's like, it's friction, right? They're pulling each other and that's going to change the angular momentum of the system because you're losing energy in that friction. And so they are going to spiral in. But I don't think much is going to survive. Yeah, I thought about that once because somebody asked me about white dwarf binary evolution, and I'm like, oh no, they're going to have horrible deaths. So I feel bad when stars.
Nick.
So when you get your data from your telescopes, do you have to correct for gravitational lensing at all, or any of the other relativistic effects?
No, not at the level that I'm working at, thank goodness. If you are looking for very low mass planets, yeah, you do have to correct for some relativistic effects. You can use exactly this is exactly what people do, the radial velocity exoplanet searches. Exactly the same technique. You're looking for the motion of the primary star in response to the planet. You're looking, I'm laughing because it's so funny. You're looking for things, you know, you want to find the Earth, you got to get down to 20 centimeter per second precision.
Jake.
I know that you have been talking about the younger stars a fair bit, but I couldn't help but notice when you were talking about the methods of measuring the mass ratio, you said that the methods that you were talking about specifically applied best to the younger stars. And I was curious what sort of changes and how you would go about calculating for the younger stars.
Oh, yes, right. The disks. Young stars with that formation scenario that I showed where they collapse and then they start to have some kind of angular momentum. And so then material can collapse into a disk along the axis of rotation. And so you end up with this nice disk of dust and gas, mostly gas. And that's where you're forming the planets. But those disks dissipate. And that's a big area of the research we're doing. Like, why are those disks, what triggers dissipation? Because that takes that disk out of play for planet formation. And so that's, sort of part of this whole story. But for the low mass stars that I look at, they're going to grow up to be sunlight-ish. Those disks dissipate within 5 to 10 million years, typically, at the most, sometimes earlier, which is one of the questions we're working on. And so the older things don't have a disk. So if you don't have a disk with CO in it, you can't actually measure the central mass. So yeah, it's just like leap where you have the young things, but not the old things. Yeah.
So I had a question on, when you were talking about, Lisa and I.
Yeah.
With the information, you said when you were using that equation that you were using an inclination of 90, for those like eclipses.
Oh, yeah.
So I guess my question would be, are you only looking at systems with the inclination of 90, or are you?
Yeah. That was actually just cyanide. It's mass, mass times cyanide cube, I think. Yeah, my mass cube, yeah, it's okay. And so, yeah, no, in fact, I haven't even bothered with the eclipsing ones. They're beautiful, they're wonderful, because you get everything. You get the stellar radii of the stars, you get the mass ratio, you get the masses. They're really, I mean, think about it, you gotta get them just at the right angle. And so for young stars, double-lined eclipsing binary young stars, there's a dozen or two. So, and I need a lot more than that. I need a lot of stars to do these kinds of calibrations of the models.
Oh, it's kind of a dynamics systems question. Stars are rotating, they have different masses or whatever. But planets couldn't possibly form if there weren't stable orbits for low mass objects around the stars. I'm just thinking that the way you can know through some of these things, if you could understand that and say, wait a second, these kinds of systems do not have stable orbits around the low mass objects.
Yeah, it depends on the binary separation. So yeah, absolutely. If a binary is really, really close, you're not going to have, you're not even going to have circumstellar material. You're just going to have maybe a circumbinary disk. And we've found plenty of circumbinary planets. So you can form planets way out orbiting both stars.
Mm-hmm.
Or if the binary stars are far enough apart that you can have stable circumstellar orbits. And those sort of the second part, the last few slides I showed were for that case, where you have binaries, but they're pretty close. So you know the disks are going to have some impact on each other, but they're not so close that there's no stability at all. And so you actually have circumstellar material, and so the planets form events.
So you said something earlier that you think are there instances, or there many of them where you have the material disk, the accretion disk that's not co-binary with the orbital plane, binary system? So is it only those that relatively far apart that happens?
That's for sure. We've seen that. Some have seen that. There are cases of that. And there's really interesting things. Just forget about binaries. Just think about a single star with a circumstellar disk that's forming planets. It's been shown that there are disks that are misaligned with the equator of the star. So, the star is rotating around some axis. You call the equator the plane, the equatorial plane of the star, perpendicular to the rotation axis. And disks have been seen tilted with respect to that. And planets have been found with these high liquidities. And so that's a whole wonderful area. And so, yeah, the ALMA program that we have, and then we're going to reapply for time for, is we want to get higher angular resolution. We want to use ALMA and kind of spread out further, so we have even better, higher resolution, so that we can get enough, we can resolve the actual disks very, to at least 2 or 3 sigma, hopefully more, and measure the exact inclination. So we're looking for that in these systems. Deadline is April 25th. Thank you.
Well, thank our speaker again.
All right, how do I do this without making it unhappy?
Let's see, let's do this first. Oh, great. Okay, so we are going to
Stop
I'm not-
recording.
Talk to you next